Hello, everybody. Welcome to the World Expert Series, series that is being held and hosted by Kachikena, where we're bringing experts from around the world to share ideas, but more importantly, to share tools of the trades that they are in. And today we have an expert in machine learning, in particular in reinforcement learning. He'll share about the theory of reinforcement learning, as well as give you practical and a practical exercise for you to get a taste of what reinforcement learning is about. So we're very excited to have Mr. Avalpreet Bra, and I will let him introduce himself, and then we'll move on to the session. But um, before we move on, I want to make it clear that this is supposed to be an interactive session, so you can ask questions during the presentation itself. And afterward, there's also going to be a special Q&A session where you can ask questions, but we encourage you to just ask the questions during the presentation. That way, we don't forget. So we wanted to be very interactive and interesting and fun. Okay, so let's get started.
Hello, everyone. A very good afternoon. My name is Avalpreet Singh, and I'll be presenting today on the topic of Introduction to Reinforcement Learning. I'm doing my Master's of Engineering here at NTU, and I've been working with reinforcement learning algorithms for some time now. And I would like to share with you all guys what I've learned so far. So let me share my screen. All right, so we'll start with the introduction. So the first thing that comes into mind is what is reinforcement learning anyways. So I would like to think of reinforcement learning as a learning to, take an optimal action in any particular situation so that the action leads to certain rewards that are maximized. So it's like learning what action to take in a given situation so that the rewards are maximized. And how is it any different from any other machine learning languages or like any other machine learning algorithms? Is that, for example, in supervised learning, we have the right answers or the labels itself beforehand, and we try to learn a function or a mapping from input space and the labels. But in case of reinforcement learning, the learner is not told which action to take, but he must discover which action yields the most rewards. So there are a bunch of options that are available with the learner or the agent as it is called. And he or she or it takes that action, and then it receives a reward out of that action. If that reward is high, then the agent learns that it is good to take this action in this particular situation and vice versa. So something that is very closely related to reinforcement learning is something known as the sequential decision making. Now, you see this picture here. There is the person. Let's say, let's imagine a situation here. Let's say this guy has come to a random new city and he needs to go to his home. And right now he's at his workplace. He doesn't know the exact path to his home, but let us assume that all the paths eventually lead to his home. However, the paths may vary on depending on the length of that path. So he's repeatedly facing this kind of situation that when he starts from his workplace, he goes to an intersection, and at intersection he has to decide whether he needs to take a left turn or he needs to take a right turn. So in this case, the situation here is the intersection that he has to face, and then the action space becomes whether he needs to turn left or right. Doing this, eventually he will reach his home by taking a particular path, but the objective of the person should be that he needs to take the shortest path to home. So it would be like if we quantify this objective in terms of reward, it will be like maximizing this reward, which is negative times total path length to the home. So when we maximize the negative of any value, it will be like we'll find the shortest path because that will be the value which we need to get. All right. So how do we model sequential decision-making processes? So uh, generally, this is a very standard framework of modeling a sequential decision-making process, which is known as a Markov decision process. Now, let us say that we are in any particular situation, like in previous example, we were in at an intersection. From now onwards, let us call that situation to be the state. All right. So let's say we are in any particular state st, and t is the current time slot. We have a bunch of options or actions, let's say left, like turning left or right. We take any particular action at in that state st. This will yield some reward rt plus 1, and we'll be transitioning into another state, which will be the next state or the transition state st plus 1. Now, let us take a simple scenario. These states, actions, as well as rewards must belong to any of these finite sets, which means that the state can either be S1, S2, or S3 and cannot be anything else. So while transitioning, let's say the person starts at state S1, goes to state S2, then goes to state S3, and then back to S1 or something. Anything is possible. Similarly, actions have to be either A1 or A2. So this is a very simple case. Since the state space, action space, and the reward is all finite, this kind of decision process is known as a finite Markov decision process. Okay, so now let's move to the dynamics of the Markov decision process. What do we mean by dynamics? So basically, dynamics is denoted by this probability distribution function. Here in this case, it is a discrete probability distribution function. That if you started in state S, let's say, and you took an action A, what is the probability that you will end up in state S prime while taking or getting the reward R? So this probability, which is conditional to this condition, is known as the dynamic function of this Markov decision process, or sometimes the dynamics of the environment. This is in simple notation, it is denoted like this. All right, let's take an example. For example, in our finite Markov decision process, we have two states, which are S1 and S2. In any state, we can take only two actions, which are A1 and A2. Once we take that action, we are either going to get reward R1 or going to reward R2. And eventually, again, we are going to transition into any of these one of these states. Okay, so we can summarize all this using this table. For example, let's say we fix that we are always going to start in state S1 and we are going to take action A1. Now, we can either transition to state S1 again, or we can go to state S2 while getting a reward of R1 or R2. So there are four possible combinations which are given in this second column. All right. For any particular transition, let's say state S1, we took action A1, went to state S1 again by getting reward R1. We have this transition probability, which is the probability of going to state S1 again, getting a reward R1, given that we were in state S1 and we took action A. This is nothing but the conditional probability, but in terms of reinforcement learning, we call this the dynamics of the MDP or the dynamics of the environment. All right. Now, next important concept is the transition probability. All right. So it's like this. You have a finite set of rewards. If you sum all the state transition probabilities with the reward, let's say R, and you sum it over all the possible values of reward, you get the probability of transitioning into state S once you start from state. Let's say in this case, you get the probability of transitioning to state S1 when you started in state S1 and took action A1. All right. So here we are not caring about what reward we are going to get. It's just like what is the probability we are again going to end up in state S1. Okay. In another possible scenario, we might be interested in what is the probability of, let's say in this case, what is the probability of getting reward R2 and while we were in state S1 and we took action A1. All right. So this is like a basic overview of dynamics of the Markov decision process. So far what we have seen is that there are three important components to a Markov decision process. One is the state, second is the action that we take, third is the reward, and then this happens in a sequential manner. We are in a state, we take action, we get a reward, and we go into next state. And while doing so, there is a probability involved. We can go from any state to any other state, but there is a the probability that is involved with this transition is given by the dynamics of that ability. All right, let's move on to next concept, that is of return and policy. Uh, okay, when we repeatedly go in these transitions, let's say we start in S0 and then which was the initial state, we took action A0, we got reward R1, and then we moved to state S1. Again, we took action A1, got the next reward, and so on, right? If we eventually terminate and then stop these transitions, this kind of tasks are known as the episodic tasks. For example, in our initial example, where we were starting from our workplace and going to our home, and the series of the intersections were our states, going to left and right was the action that we are going to take. Reward in that case was the length of the path that we are going to take till the next intersection. And finally, when we reach home, that is our terminal state. So this is the episodic task. However, all tasks need not be episodic, and this transitions may continue in a continuous manner forever. For example, let's for sake of simplicity, let's keep the episodic task as of now. For example, let's say you are in state ST. Now, while being in state ST, if somebody asks you what is the rewards that you will observe here on till the termination of the states, that is the sum of all the rewards that you are going to get from state ST onwards, that is RT plus 1, RT plus 2, RT plus 3 till R capital T in this episodic task. This sum is known as the return. All right, this is just the definition. The dot on this equality sign means it's a definition. That means it's not derived from somewhere, but we start this thing from here onwards, right? So this is how we define return. All right. So next important concept is that of policy, which is, I would say, the most important concept in reinforcement learning, as well as the objective of any reinforcement learning task. So it is like when you are in any state ST, what action should you take, or what is the, like in particular there are two types of policies. In this case we will study the stochastic policies. Here it is the probability distribution over the entire action space. For example, let's say you had only two actions, A1 and A2, and you had, let's say you were in state S1. So in state S1, what is the probability you are going to take action A1, and what is the probability that you're going to take action A2? So that is known as the policy. This policy is basically the main goal of our reinforcement learning task, and we, in upcoming slides I will show you how we will try to learn the best possible policy that will lead us towards higher rewards when we implement that in a sequential manner. All right, before moving, we will also cover the continuous task, where you don't have any concept of terminal state and these transitions keep on happening. In this case, you see that you cannot add the rewards directly, because if you keep on adding these values, this value may blow up to infinity. And then in order to prevent that, you add this discounting factor, which is any value between 0 and 1. And this ensures that the overall return, that is the sum of these rewards, is finite. All right. So exactly. So that is the goal of reinforcement learning, that at any time instant, which policy will lead to higher returns in average. All right. So let us discuss this in more detail using a backup diagram. Okay. Assume that you started in state ST. We are sticking to our old example where we have two states, the S1 and S2 state. And we have two possible actions that we can take, that is A1 and A2. And there are two possible rewards, that is R1 and R2. In reality, in practical, there will be a lot of states and actions as well as rewards, but just for sake of simplicity and understanding the concept, we'll keep things simple. All right, so let's start with state S1. Now we can either take action A1 or A2. Corresponding to each action, there is some probability that is involved, right? That is the policy which we are going to learn eventually. So that policy, which is denoted by pi here, is a conditional probability that you're going to take an action A1 given that you are in state S1, or you are going to take action A2 given you are in the state S1. So the probability of taking action A1 is 70% in this. So this policy need not be the optimal policy. It's just like you can have any values this, but our goal is to learn an optimal policy using certain algorithms, which we will discuss later. All right. So once, let's say you have taken action A1 out, like which is denoted by a solid line here, and you didn't take action A2, which was denoted by a dashed line here. Now, once you take action A1, there are four possible scenarios. You can either go to state S1 by observing reward R1, or go to state S1 by observing reward R2, or go to state S2 by R1, and finally by like going to state S2 or by observing reward R2. Now, these all possibilities are decided by the dynamics function of this Markov decision process, which is given by this probability distribution function P, which we have explained in the past. So let's say you took this solid path. So if you started in state S1 and then you took action A1, and once you had taken action A1, you observed the reward R2, and then you ended up in state S2. The probability of this happening is 0.7 times 0.4, that is 0.28, right? So that is the probability of this thing happening. All right. So each of these branches is possible, and this solid line is just one possibility. And as you can see, you started in state ST. This is one step transition to next state ST plus one. This keeps on happening. If it is a continuous task, it keeps on happening forever. If it is an episodic task, it will eventually end somewhere. All right. Now we'll move on to some really important concepts of state and action value. Okay. To recall, what is the definition of a return? The definition of a return is it is the rewards that you are going to see from now onwards, but with a discounted factor gamma, because since if it's a continuous task, you need to have this finite value of the overall sum of these rewards, which is the return here. Okay. Now, okay. Okay, that's a good question. So discounting factor always remains a hyperparameter in your modeling. So it is up to you to decide, but generally people keep the value of gamma to be 0.9, right, towards higher discounting factor. Actually, if like to be more specific, the discounting factor actually decides how far ahead do you want to look. As you can see, the values of gamma increases, like it's one here, then gamma square, gamma cube, and also on. So if you keep a very small value of gamma, you are not going, the effect of terms after some values of gamma are not going to significantly affect your total return value. So we call this kind of system as myopic systems. However, if you keep value of gamma equal to 1, that means you want to observe all the rewards till the end of this task. So it discounting factor decides the vision that we want to look ahead. All right. So we'll move on to the state value of this, the state value concept. Now, starting in any particular state, we will have a sequence of rewards that we will observe, right? But these rewards are random variables, because uh, for corresponding to each reward there is a probability involved. If you go back a couple of slides, I had shown that uh, from the transition probabilities or the dynamics of an MDP or environment, we can find the probability of getting a particular reward and next state, given we are starting in a state and action. All right. So since it's a random variable, we can only get the expected value of the rewards that we can get in the future, and the sum of that rewards is the return value. So the expected value of the return, once you start in state S, if you follow the policy pi, is defined as the state value. Now, the intuitive meaning of a state value is it's like how good are you, how good is it to be in this current state. For example, if you are in current state S, you are going and you are going to, you have decided that you are going to follow the policy pi. How, what is the rewards that you will be getting on average when the episode ends, or like in a long run. So that is the value of any particular state. A similar concept is that of action value, which means that given in a particular state, you have to decide what, let's say you take an action A and you want to quantify if it is a good or bad decision. So an action value tells you what are the expected rewards you will see once in a state as you have taken action A. That is given by this diagram. State values are denoted by V pi s and action values are denoted by Q pi s A, which means in state as, if you take action A, what are the average rewards that you will be seeing in future if you follow policy pi. All right, so let's discuss state value in more details. We have our own backup diagram for that previous example where you had two states and all that. So let's say you had this state S and there was a policy pi initially, which helped you to take any action. Let's say you had some probability of taking action A and you took that action. Now you're going to observe a reward and go into next state. All right. Now consider this point. Let's say you reached here, which is the state S prime. Again, this S prime is going to be one of the values of that finite set of states. Like, let's say if it was S1, S2, so it's going to be either S1 or S2. But you have transitioned into next time step. Initially, you were here, you took an action, you got reward. Now again, you are in any of one of those states, but a transition has happened. Now, if you see from that point onwards, if it is a continuous task, that means the value or the expected rewards that you are going to see from now onwards will again be denoted by this value function v pi s prime, which means starting from s prime, what are the rewards that you will see in future. All right. Okay. So since we will have similar value functions for each of these states, and we also have the probability of these two pair, like getting this reward R, that is the immediate reward, and transitioning into state S prime, that is given by the dynamics of the MDP. So using these two things, you can get the expected value of rewards that you are going to see from this point onwards, which is denoted by this black dot. All right. And if you are familiar with the concept of expected value of random variables, so it is the probability of seeing that random variable times the value of that random variable. And we add all such possible combinations. Let's say if you have two random variables, R1 and R2, and you have probability PR1 and PR2 for them, then the expected value of that random variable is PR1 times R1 plus PR times R2. All right. So from this point onwards, the expected value of rewards is going to be this value, where the first term is the probability of seeing this combination of R and S prime, or the probability of taking this path. And the second term is the reward associated with this path. The immediate reward is given by small r, and the after taking that reward, you transition into S prime, and then thereafter onwards, you have the expected value of rewards, which is given by V pi S prime. Since it is a continuous task, we are adding a discounting factor in this. So you have this value of the expected reward, and you have this probability of seeing this reward. So from this point onwards, the expected value of the reward is given by Q pi SA, which is also the as per the definition is the expected action value. If we go one step ahead with similar ideology, you see the term behind this sigma value is Q pi SA. So we have, for every action, we have its expected value, right? So that expected value is given by this term after this sigma. And we also have the probability of taking that action. And this will give us the expected value of state S. That means from state S, what is the reward that we are going to see in average? All right. So I know this is a little hard to grasp, but it will become clear in subsequent slides. Okay. So what is the purpose of doing all this? The purpose of doing all this is that we don't know what the values of states are. All right. But we know that all these states follow this, the final equation, that this is the like the relationship between all the state values, right? We don't know what the values of state are, but we know that whatever the values are, they will satisfy this relation. So this particular relation is known as Bellman's equations, because you will see that this is nothing but a system of linear equations. You see that if we know the dynamics function and probably this policy pi, which is decided by us on our own, we have these two variables alone. Let's say it's a two-state system. V pi s1 and v pi s2 are the two variables, and we have two equations. All right. So let's say we want to estimate the values of v pi s1, so we can solve this system of linear equations to get the basically, we can solve these Bellman equations to get the state values of that Markov decision process. All right. Okay. So coming to the main task of reinforcement learning, the main task is to find the optimal policies and optimal action values. All right. So a policy pi is said to be better than any other policy pi dash if the state values for all the states while following the policy pi are more than the state values of all the states while following the policy pi dash. What this means is, in simple terms, let's say you have a policy pi and it is taking you along this trajectory, which is given by this green line. And then you have policy pi dash, which is taking you along this red trajectory given by this red lines, right? So when you are following these two trajectories, you will be observing some rewards along the way, right? So the expected value of rewards that you will observe while starting in state S, if for any state S, if it is always higher for policy pi than policy pi dash, then policy pi is going to be better than policy pi dash. Let us elaborate this more. For example, you have x-axis. X-axis is represents all the possible states. I have just shown it in a continuous space, but you can have discrete values. Let's say these states can take any value. It is denoted by this x-axis. And y-axis is the value of that state. All right. So for any particular state, you have a value of that state, which is given by this y-axis. Now, if you follow the policy pi dash, this curve in the red represents the values of all the states. That means if you start in state S, you will observe this the expected return that you are going to observe is given by this curve, and the value can be seen on the y-axis. Now, a policy pi is better than pi dash if is actually strictly better than pi dash if this policy is always higher than the policy which is given by pi dash. That means the value of any state is always higher than the value of that particular state if we follow the policy pi as compared to following the policy pi dash. All right. Now, naturally, if we continue improving policies, we get better and better policies. There is always a policy that is going to be the optimal one, above which there is going to be no policy. Otherwise, the very purpose of the optimal policy fails. So that optimal policy is going to be a policy for which this value of any particular state is going to be the highest as compared to any other policy, no matter what. So that PISA, so there can be obviously there can be more than one optimal policies, but let's say there is one optimal policy which is given by this orange line and this denoted by pi star. So for pi star, we denote pi star is greater than or equal to pi is greater than pi dash. This means that policy pi star is better than pi and pi is better than pi dash. All right. Now let's say oh, that's a really interesting question. So in that case, let's say, Christopher has asked this question that if green line is sometimes higher and then red line is sometimes higher. So in this case, pi is not cannot be said to be better than pi dash, first thing. Second thing, you can find a policy, third policy for first half, you can take it as the one for pi, and then for second thing, you can take it as pi dash. So this third policy is going to be better than both pi as well as pi dash. So yeah, that's what is the concept of better and better policies. All right. So then next is the optimal values of each states. All right. So let's say you start in state S and you follow policy pi. So whichever policy is going to take you towards the highest rewards in the end is going to be the optimal value of that state. And of course, that policy also will be the optimal policy. Okay, so we will be deriving the Bellman optimality update in this slide. It is very similar to Bellman equation. So let's say we were following policy pi star, similar to any policy pi. It is going to be like any other policy. And after one transition, we denote the value of that state to be V star S. Now the value of the starting state is V star S. Now we want to see the relation between these two. Like in Bellman's equation, we found the relation between any the state of values while following any policy pi. For this optimality Bellman optimality equation, we'll find the similar kind of relation. Okay, so like as explained in the past, the action value or the expected value from this point onward is going to be this product. This is the sum of probabilities of seeing that reward and action, the reward and subsequent state, and the actual value of that reward and that subsequent state. All right. So once we have this, imagine we are standing in the state S, and we know that taking one action will lead to some expected reward in the upcoming states that is given by these action values. Now, an optimal policy will be the one that will pick the action that will take us along that path, which will eventually lead to the highest action value, right? So if this is the path it has to take, which according to the action or the state values here. So V star as prime are the state values, and this whole expression is the action value. So whichever action is going to have the highest action value, our policy will be only optimal if it will pick that action, right? Otherwise, it will, if it picks any other action, it will lead to a suboptimal value of the rewards that we will see in future, and then we cannot call it the optimal policy. All right. So in this case, let's say if we takes that optimal, if the policy is optimal, we take that action. So we are going to get that optimal reward, or that value is going to be the optimal one, and which is noted by V star as. This optimal value is going to be the maximum action value. That's it. Because while taking action, you don't observe any reward. All rewards are observed after you take an action, right? So if you have all the action values, if you just pick the best action value, you have the best action value. Note that the state values in this case have to be optimal, right? If you, in that space, if you pick the best action value, you have the best state value for that particular state, right? So this is known as a greedy way of finding the optimal policy, and we will use this in our policy iteration algorithm, as you will see in subsequent slides. So this particular equation is known as Bellman optimality equation. Okay. So let's discuss this Bellman optimality equation. It's similar to Bellman equation. The only thing is that the summation over all possible probabilities missing, and we are just, instead of getting the average value over all possible action values, we are just picking the action value with the highest value for that particular state as, and taking that action A. So that is the highest action value, I would say. Um, and then if you see this, this is nothing but a system of nonlinear equations because of this function of maximum one, right? So we have these like bunch of nonlinear equations, and in principle, these equations can be solved by using any standard nonlinear solver, but these computations are generally computationally expensive. Secondly, we also need to know this transition probabilities or the dynamics of this environment. Let us assume we know this transitions, right? Even then, it's difficult to compute these directly using a solver. So we use dynamic programming to solve this. So basically, what we will do in next section is we will try to get the optimal state values as well as try to learn the optimal policy using one such algorithm, which is known as policy iteration, which is the most basic one in the reinforcement learning task. All right, before moving that, um, assume a situation where you already know the optimal state values, which are these V star F prime, right? So if you know these state values, you also know the optimal action values, which is given by this entire expression, uh, the expected reward from state S, and you take A. We have discussed that a couple of times. So this is the optimal action value, and you need your policy to be designed in such a manner that, since let's say it is a stochastic policy and it gives the probability distribution over action space. Let's say you have two actions, A1 and A2, and your action A1 leads to let's say eventually the state value or state action value is, let's say, 5, and action A2's state value is 3. So what you will do is you will make the probability of taking action A in state as 1, where if let's say A1 was going to take a higher reward, so you will make probability of A1 given as 1, and all other probability for all the other actions you will give that probability as 0. So for the action that leads to the highest action value, we keep the probability 1. For all the other action values or all the other actions, we keep the value of the policy as 0, which is the probability of taking that action, right? Okay, so in this section 2, we will cover the policy iteration algorithm, where we will try to learn this optimal state values first, and then secondly, we will try to learn the optimal state value, state policy, sorry. All right, so so the problem at hand is we want to learn the values of state, okay, which is given by V pi s for all the state s and a given policy pi. All right, we don't know what the values are, but one thing that we know is that they satisfy this Bellman, with these Bellman equations. That means all these values satisfy this system of equations. From that, we can find the state values. All right. So what we do is we start with arbitrary values of this state. Let's say we give it random values. Let's say we initialize every value as 0, and then we use this because we have this update rule. We use this update rule to get one step update in each value of that state. For example, on the right side, you will use all the old values of states given by Vk as prime, right? And using all those old values, you get the new value of state as at the next time step, that is k plus 1. Okay, if you do this in a repeated manner, eventually you will see that the values, the change in the value keeps on reducing after you keep on doing this, and it can be shown theoretically that these sequences of vks will eventually what they call as converge. That means they will not change substantially, and at k is equal to infinity, it will not change at all. However, for our algorithms, we will not implement this till infinity. We'll be keep on we'll just terminate this algorithm after a finite time. All right. Next is the policy improvement. Now, what we have done is, for a particular policy pi, we have learned the policy values. Since we know the policy values, that means we know the we know if we have learned the state values. Since we know the state values, we also know the action values. And since we know the action values, we can always make the the policy greedy with respect to the highest action value. That means uh, improved policy is made greedy with respect to the evaluated action value. So I'll explain this in detail. So V pi S prime are the state values that we have learned using policy evaluation, like shown in the previous slide, right? So you start with the random values of state, you do the policy evaluation, you get, and you keep on repeating it, this Bellman update, until you converge and get the like some value of the state for that corresponding value of pi. So that is the state value. Using that state value, we get the action value of that state for taking that action A. From that, we choose the action which leads to the maximum action value, which is known as a greedy decision. For that particular action A, we allocate the probability of taking that action A for state S as 1, and pi dash is our improved policy. And for all the other actions, we keep it as 0. So we do the state policy evaluation, we do the policy improvement. Now we have a new policy pi dash. Now for that new policy pi dash, again we will do the state evaluation, and again we will do policy improvement. This process is known as policy iteration. So you start with pi 0, which is any initially you know you can initialize any policy in starting. The only thing that you need to take care is that it satisfies the condition that the summation of over the entire action space has to be 1, because it's a probability distribution, right? In case of discrete cases. And then the E step is the evaluation process, where you get the state values corresponding to this policy pi. Then you do the improvement over this policy, which leads to an improved policy pi 1. Then further again you do the evaluation. You keep on doing this you keep on doing this till the time that the policies are not improving as well as the state values are not. In that particular situation, you can say that you have reached to an optimal value of policy as well as the state values. All right. So this is one algorithm. There are many algorithms to do such things, but policy iteration is the algorithm that captures the essence of reinforcement learning very strongly. So you can see that you can initialize your state values with any real number. You can give it 0 values also. Okay, so we have been using stochastic policies. Even in the programming assignment after this, we'll use stochastic policies. But here, let's say there are deterministic policies as well, where pi s means with probability 1, what action you are going to take. Other all actions are having 0 probability. All right. So policy evaluation is that step of finding the state values once you have a policy pi. So this is, as you can see, there is a Bellman update here. What this loop is doing is, you need to initialize a theta value, which is user defined. That means beyond this small change, if your changes in the state values are smaller than this thing, then you can terminate this loop. Until then, you have to keep on running this loop so that you have a good estimate of your state values, right? So what it does is that for every state S, right, you have the old value which is recorded in this small v. Then you do a one-step Bellman update, right? And delta is initialized initially with 0 value. And what this step ensures is that the difference between the old value and new value and the delta is like it's the maximum possible difference. That means we need to take care of all the states simultaneously. So if we minimize the maximum gap between any two old and new values, then we will ensure that all the states have simultaneously reached to their optimal value, right? So when we keep on doing this loop forever, like at least until this delta value becomes smaller than theta, once that happens, our policy evaluation has stopped. Now we have a good estimate of our state values corresponding a particular policy that we have initialized here. All right. So once we have that policy pi, we need to see if that policy is stable. By stable, we mean that if we are in any state S, whether our old policy leads to the same action that has the highest action value, right? So the action value is again given by this expression. So what happens is that if what we do is that for the new policy, we make it greedy with respect to the newly evaluated state values. From the state values, we get the action value. We pick the action which leads to the highest action value. And for that particular action, we give the probability 1. And for all other actions, we give the probability 0. So this process continues, and this will eventually lead to the finally this transitions will stop happening, and we will get the optimal state values and as well as the optimal policy. All right. So this is the end of the theoretical part of this session. So we'll next move to the exercise or the programming exercise. I hope all of you have installed the Anaconda distribution. So I will show you a step to launch that. So I'll stop sharing my screen at this point. And all right. So in that case, you can open the Anaconda Navigator, and you have to launch the Jupyter Notebook from that by clicking launch here. That is going to take you into this particular page where like you need to go into the folder where you have saved that intro to RL, that file, that zip file. So we had shared a zip file with you all guys. So all right. All right. So once you launch the Jupyter Notebook, so you need to go into the folder where you have that introduction to RL files saved. So like in my case, it is on desktop itself. So I'll just go and open this. And in that, you can go into the introduction file. Uh, all right. So shall we begin? All right. So the assignment is like this. All right. So you are in a you're like a city planner, and this by the way this exercise has been taken from Coursera, and like you can check out, they have amazing courses on Coursera regarding all machine learning and reinforcement learning, etc. So okay, so this is basically a grid world city, and then you have a parking spot. Okay, and then parking spot has certain parking spaces, right? So let's say you have 3 spaces. So depending on that number of spaces, your states can be either 0, 1, 2 till that number of the spaces. That means uh, what that means is that let's say you have 3 available spaces. Your state represents how many spaces are occupied. So 0 means 0 spaces occupied, 1 means 1 space is occupied, then 2, 3, 4, like till the number of all the spaces are filled. All right. So that is the state. Then the price that you decide for that parking system is the action that you're going to take. The reward and next state are decided by the dynamics of this MDP that is taken care by the code already. All right. So let me give you a brief overview of this Anaconda distribution. And this, like you can develop your code here, or you can develop your machine learning models here. You need to first import all kinds of packages. Like in this particular assignment, you need just very basic packages like NumPy, etc. And there is another tools package that I have already included here that includes all the functions that are going to be implemented. All right, so you don't need to worry about all this. So let's say we run this. You can run this cell by Shift Enter. Okay, so we will go in detail in one by one with all this. So number of spaces are, let's say, 3. That means uh, there are three spaces in the parking spot. So either 0 can be filled, or 1 or 2 or 3 can be filled. So you have 4 states. All right. And the number of prizes are 3. So that means your actions are 3. You can either take a 0 action, or that means the first reward value is 0, second is 1. Sorry, first price value is 0, second price value is 1, third price value is 3. So there are 3 possible actions. The environment will help you transition from one state to another. I'll show you how. So now let's see. So you have initialized your values with 0 values for each state. So there are 4 states. Each state has a value 0. That means state 0 has a value 0 and all. So that means you can start with any values of the state. So just exploring a little more, the value of state 0 is 0, as you can see here as well. You can set the value of any particular state as, and let's say you set the value of state 0 as 10. Now your state value is of the state 0 is 10, and the state value of all the other states is 0. Summarizing all this is like, if there are 4 states, state 0, 1, 2, 3, and the value of the state 0 is 10, and all the other values are 0, right? Then you have a policy pi. uh, the policy pi is again a numpy array. It's a 2-dimensional array. The row number represents the state, the column number represents the action, and the value represents the probability of taking that action in that particular state. So if state is 0, that means the 0th row, this will tell you the probabilities of taking action 0, action 1, action 2. So as you can see, the sum has to be 1, because in any particular state, if you sum over all the possible all the possible actions, the value has to be 1, since it's a probability distribution, right? So at state 0, the value of action 1 is again 0.33. So let's say you set all the state, the state for state 0, you set the new values of picking up a particular action. So in state 0, the probability of picking up action 0 is 0.75. Probability of picking action 1 is 0.21. Picking up action 2 is 0.04. Right. So summarizing this, this is basically the policy distribution, which is the probability distribution of this policy for any state S. What is the probability that you're going to take any action? So in state S0, the action probability of taking action A0 is 0.7. All right. So this is just a plot of the same thing. So you can see that there are 4 states, state 0, 1, 2, 3. The value of state 0 is 10, as we had set here. All other are 0. All right. And then this is the policy, which is this 2-dimensional array, where the value of state, the probability of taking action 0 in state 0 is 0.75, which is denoted by this block. Since the 0.75 will be something here, so it's quite dark. All other values which are 0.33 are something like in this gray area. All right. So so if you see, there are total 4 states. There are 3 actions that you can take. And this is the transition. That means the row here represents the state that you are in. And the first column represents the reward that you are going to get when you transition from state S while taking action A. So if you in state S, you take, let's say in state 3, you take action 1. So you will get reward 1 with the probability of 0.12. You will get reward 2 with the probability of 0.15, right? So this is nothing but that the dynamics of the MDP, or the state transition probabilities, which we were discussing back then. Okay. So for any other combination, the value is 0. All right. So these are the state values, or the transition probabilities. Sorry for that. Okay. So this is the basic setup. And in the assignment, you are supposed to implement the policy iteration algorithm, where I'll first show you this section that you need to implement. But I think for today's session, I'll give you the solution as well. You can try back at home, and after going through the slides and doing this introductory, the introductory Jupyter notebook file first, then you can transition to this assignment. So we'll just import all these things. Basically, there are two steps in any policy iteration algorithm. One is the policy evaluation, and second is the policy improvement. So in policy evaluation, you take the old values of states and you use this policy update, this Bellman update rule to get the new values of each state, right? So there is one code that you need to implement for this Bellman update. So if you check this function, the evaluate function, this is nothing but same to the evaluation function that we saw in the summary of policy iteration algorithm, where we have delta and theta here. So theta is user defined, and what this does is that it will keep on running this code until the values of each state is the change in value of each state is below theta. Okay, so for there is one line of Bellman update which you need to cover in this code. This is just like updating the state value of each state. For example, in state S, V is the old values of those state, pi is the policy, and gamma is a discount factor, and environment helps you get the transitions from one state to another. If you see here, when you transition from state S and taking action A to S prime, and you get the reward R, Vs prime are your old values, and rewards you get from the first or the 0th column of environment dot transitions, and these the probabilities you get from the second column, right? As you can see here. So the first column is the reward that you get while taking the action A in state S, and this is the probability. So this first column is corresponding to this value, and rewards is corresponding to the first, this 0th column, and Vs prime are old values that are stored in this V vector, and the pi value is given in this pi numpy array. Okay, so you need to do, basically you just need to implement this line using numpy here. All right. So in this case, we'll be using 10 spaces, and then there will be 4 prices here. And that means the states are going to be 11, and the actions are going to be 4. Okay, 0, 1, 2, 3. And all the values are initialized with 0. Now the policy is such that uh, no matter what state, the action, the probability of taking action 1 is 1, and all the other probabilities are 0. All right. So once you complete this Bellman update and you run this equation, this cell, what you will see is that you will get the converged values of each state corresponding to a particular policy pi. All right. So in fact, I'll just move on to the solutions page, and then I'll show you how this thing is running. So we are running these states. So I will show you the, I will also discuss the answer as well. So basically what you are doing here is uh, just take this particular value from here onwards, right? So that particular value is the I have used the variable u to denote that. So you initialize that with 0, and then for each action you need to update this value by adding it in a loop, right? So for each action A, this loop is running and you're adding these values. All right. So as I've already told, so V is the old value, gamma is the discount factor, and environment dot transitions first row represents the reward, and the first column, which is given by 0, represents the reward, and the second column, which is represented by 1, is the probability of that transition. If you multiply these two and add, and then you get this Bellman equation update rule. All right. So once we run this, and I will show you this thing. So this is the state values. So initially, you remember the state values were all initialized to 0. After running this policy evaluation, till the values converge, we get that the new state values corresponding to this policy pi, which will always select action 1, no matter what state we are. We get um, these are the state values. So what this means is, no matter what is the capacity, the occupation value of any parking space. For example, there are 10 vacant spaces. So no matter how many spaces are occupied, we keep the rate fixed at 1. Okay, if we keep the rate at fixed at 1, the reward that we are going to get on average are given by this, if we start in any particular state. Okay, so that is the meaning of value of that particular state. Next is the policy iteration algorithm to improve the policy. And then that involves again two steps. One is the policy evaluation, which we have already implemented. Next is to improve the policy. In this, you just need to make the policy greedy with respect to the new action values. So you had these old state values, which were given by value V, and from this you get the action value using this, again the Bellman update. You store all the action values in any for any particular action A. You store the corresponding action value in this numpy array or a vector QS, right? So QS A will have the action values corresponding to each action. Now we need to pick the action value which is maximum, and for corresponding to that action we will give the value of that policy to be 1. For all the other actions, we will give the policy of that value of that action as 0. So the probability of all the other actions other than this action for which the action value is highest is going to be 0. Only for this it is going to be 1. Okay, so once you make this policy greedy, you get what are known as like the optimal values of states as well as the optimal policy. Okay, so you can see that these values or the state optimal state values will, first thing, it will be higher than any other policy. You can see that for all the state values it will be higher than these values, first thing. Second thing, the policy has changed. So initial policy was, what we initialized was that no matter what is the state, we are going to take action 1. Okay, but now we have seen that if the parking space is occupied till 8 value, like for example out of 10, if 8 spots are occupied, we'll keep the lowest fares. That means we will still encourage people to come. Okay, but if it's 9 or 10, that means if it's already almost filled or filled, then we will keep the prices higher so that less people eventually come, and that increases our overall objective of gaining higher rewards. So yeah, so then this thing terminates here. So this corresponding to state 0, this is the optimal state value, and the optimal policy says that in state 0 you need to take action 0. And this is a table that gives what are the action value, the actions that you need to take corresponding to a particular state. All right, so that's it for today's session. So thanks for your attention, and keep learning. I hope we'll come up with a new session with higher and advanced level of reinforcement learning algorithms. So I hand over to Christopher again.
this is more supervised and other kinds of machine learning. So it's very nice for you guys to be introduced to it as well. But we also believe that there might be a lot of questions, so this would be a good time for you to ask those questions. Any questions? Okay, so I want to ask so this is not about implementation itself, but right now, today, what's the biggest reinforcement unit?
All right. So reinforcement learning got all the attention after the success of AlphaGo. So Go is basically a game that is played in Korea, and there was this a team from DeepMind that developed this algorithm based on reinforcement learning, where using the experience of playing this game Go, they developed this on this reinforcement learning framework, and the algorithm got so better that it defeated the world champion. So that is where all this media attention and all the shift towards this particular algorithms and this, I would say, paradigm of thinking in this direction started. However, sequential decision making has been there for a long time, and people earlier used modern predictive control and other ways of doing sequential decision making under uncertainties. But reinforcement learning is a very new, I would say, recent, I would say, the newest one of these all paradigms or way of looking at these sequential decision making problems, where the ultimate goal is to learn a policy, or like what is the optimal action that we need to take in any particular state, so that our rewards get maximum when we keep on taking that actions. Yeah. Well, that's an interesting question, and I we certainly learn from our experiences. For example, when a child is born and then he learns to walk, nobody tells him what is the right way of walking. He learns it from his experience. He tries a certain actions, and whatever leads to higher reward. In that case, the reward is how long he can stand, or how, you know, how long, or how what distance can he cover. So that in that term you can say that, yeah, reinforcement learning is one way of describing how humans learn new tasks, at least at the very beginning stage, I would say. Yeah. Yeah. Okay. Thank you for having me.
Okay, so that was for now. The one extra series will continue every month. President will bring an expert from somewhere in the world to share about the techniques and tools that they're using. The point of these series is really to highlight a very important thing that is to say, the tools that people are using here in Singapore, in the US, in China, wherever, those tools you guys also have available. In other words, the tools are about the same. So that's why we're presenting these ideas not to say that you can have them here. The point is that you have those same tools. You know, this guy has been doing research, really advanced research, right? But all the things we spoke about today, you too can find them tomorrow or today if you go online. In other words, our access to the same tools. So we need to be able to build therefore advanced applications like anywhere else in the world. That is the point of all of these talks we're going to have in the next upcoming months, to remind ourselves that we have to use the matter of putting them together to solutions for society. Okay? So that's it. Thank you.
Okay. Thank you for having me.